All right, so we've got a couple of lessons left. They each have to do with the probability of multiple events happening. But there's going to be a couple key words that will make the process of finding that probability different between one type versus another. So today we are going to talk about independent versus dependent events. You might see this elsewhere as like the multiplication rule. And so first let's just talk about what independent versus dependent. I don't know why I keep saying appendant. Oh my gosh, you guys. Whew. All right. So independent events are two events in which the occurrence of one event does not affect the occurrence of another event. Okay, so again, like that's, I mean, just think of the word independent. They have really nothing to do with each other. If I want to know the probability that I like pick a purple flower from my garden and the probability that I pick like a tomato from my vegetable garden, well, my flowers have nothing to do with my vegetables. So that would be an example of two independent events. And so then for dependent events, that's just the opposite. Again, that key word here is depends. So one event depends on the other. Okay? So the occurrence of one event does affect the occurrence of another. Shorten that a little bit. Okay, and so some key words that you want to look for when you are determining whether two events are independent or dependent is to think about, are you putting something back? Are the two events completely unrelated to each other? Things like that. So for this first example, again, it says tell whether these two events are independent or dependent. So this as a box of granola bars contains an assortment of flavors. You randomly choose a granola bar and eat it, and then you randomly choose another bar. So I want to know the probability, and if I wrote it out, it would look like this. The probability of coconut, then cranberry, right? Whatever's in your parentheses is always what you're finding the probability of. So this is two events. So now I want to think, does one affect the other? Okay, so if you read the sentence again, it says a box of granola bars contains an assortment of flavors. You randomly choose a granola bar and eat it. Okay, so if I want to know the probability that I choose a coconut almond bar first, so let's just say there are like 6 bars of each. There's 12 total bars. So then I would have a 6 in 12 chance of picking coconut. Because there's 6, there's 12 total. But after I pick that bar, I eat it. So when I find the probability that I choose a cranberry almond bar second, I don't have 12 bars to choose from anymore. I only have 11. So these would be an example of dependent events because I'm changing my final amount in my probability. So I would multiply that. I would still have 6 cranberry almond bars, but I only have 11 to choose from instead of 12. You are not going to actually find this probability. We'll do that in a little bit. But this just kind of shows you that this would be dependent events. Okay. So in number 2, it says you roll a 6-sided die and you flip a coin. So I want to know the probability that I roll a 4 and then I roll tails, or flip tails, I guess. Okay. Well, if I want to find the probability of rolling a 4, that would be a 1 in 6 chance. Well, that roll has absolutely nothing to do with what I flip on the coin. Okay, so that would not affect that probability. I have a 1/2 chance of doing that. So that means that these two events are independent of each other. They don't have anything, the outcome of one does not affect the outcome of another, okay? And so you find the probability. So I put these two examples here. I'll just kind of write out in words. But you find the probability the same. You always multiply the 2 or 3 or 4, right? You could have 4 events that you're trying to find the probability of. Some may be dependent, some may be independent. But regardless, you always multiply their probabilities together. The one thing that you have to change for dependent events is definitely the denominator, possibly the numerator, which we will look at. I think I put an example, yep, right there, okay. So when you're finding the probability of independent events, so if A and B are independent, then the probability that A and B both happen is going to be the probability of A times the probability of B. Okay. If you're finding the probability of 2 dependent events, then we use what's called a conditional probability, which is like under the condition that this happened. Essentially what that means is make sure you change your denominator. Make sure you change the total that you have in your sample space. So the probability that A and B happen would be the probability of that first event, so that doesn't change. But then the probability that B happens given that A happened. So that's what this means. So again, I'm just going to kind of put down here, change denominators. So I don't want you to necessarily like worry about like these equations. They're not really equations. They're just kind of like methods that you use to find probability. Okay. All right, so if we just look at several examples here. So it says, as part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. Okay, well, first we need to determine is this an example of an independent or dependent situation? So the first event is that I roll a 5. Okay. So I'm not taking the 5 away for my second spin. I'm not taking it out of the equation for that second probability. So this would be an independent example. And the outcome of my first spin does not have anything to do with the outcome of my second spin. So I want to know the probability that I roll a 5 and then a number greater than 3. Okay, well if there are 8 numbers on here, there is only one 5. So I have a 1 in 8 chance of spinning a 5. Then I have got 1, 2, 3, 4, 5 out of 8 values that are greater than 3. Okay. So my final probability is going to be the product of these two fractions. So remember, when you multiply fractions together, you multiply straight across the numerator and straight across the denominator. So 5 out of 64 would be my final probability. So you can either leave that as a fraction, or the percent would be about 7.8%. Okay. All right, and so let's look at a couple other examples here. So this says a bag contains 20 $1 bills and 5 $100 bills. So first I'm gonna say that this is 25 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. Find the probability that both events A and B will happen. Okay, so here's the key part of this. I set it aside. So that means that I am changing what I have to choose from in my second event. So if I want to find the probability that I pick a $100 bill and then another $100 bill. Okay. Well, the first time I have 5 out of 25 bills to choose from. But if I set that aside, then my next draw, I only have 4 $100 bills out of 24 total. Okay, so when you multiply across here, again, because when we're multiplying like the 25 and the 24, that's obviously going to be a pretty big number. So I would recommend, in terms of like leaving your answer as a fraction, to go ahead and simplify first, because it's going to be a lot easier to simplify these smaller fractions than the bigger ones. So 5 out of 25 is going to be 1/5. That's going to be 1/6. Okay. Even if you don't reduce it all the way at first, it's going to make it easier still at the end because your fractions are going to be smaller. And so this would be a 1 out of 30 chance. 1 out of 30 is about 3.3%. Okay. So there's a pretty small percentage that you'd pick 2 $100 bills. You're going from a 20% chance, and then what's 1/6? Like 16-ish? Yeah, 16.7%. But 2 in a row is only 3.3%. Okay? All right, so I might actually have you pause the video if you want to. Try some of these on your own, this next group. All of these are without replacement. Okay? And so that means that you're taking away an option for your second draw. So if you want to try these, pause, see how you did. All right, so for these examples, the first thing we need to do is figure out our total. So I've got 5, 3, and 2, so that's 10 marbles. So for all of these examples, your first event will be out of 10. And then since we're doing 2 options, that means that our second fraction is going to have a denominator of 9 because I'm not replacing it, and so I only have 9 marbles left to choose from. Okay. All right, so for this first one, the probability that I pick a purple is 5 out of 10. Then if I set that aside, the probability that I pick an orange is only going to be 2. Well, I shouldn't say only. I still have 2 oranges, but I only have 9 left to choose from. I'm going to go ahead and simplify that first fraction. So 1/2 times 2/9 is going to be 2 over 18, which simplifies to 1/9. And so when I do the percent, if you want to do that, that's going to be about 11.1%. All right, so the next one, probability that you pick orange, then green. And so orange would be 2 out of 10 this time, because I'm going back to, these are all different examples. And then if I want to pick a green, I've got 3 green marbles, but only 9 left to choose from. I simplify those fractions first. 1/5 times 1/3 would be 1/15. And then 1 out of 15 is about 6.7%. All right, so 2 oranges. Now it's important to understand that this means 2 back to back. So this is another way of saying orange then orange. Kind of like this one, 100 then 100. So the probability that I pick 2 oranges in a row, well, my first probability would be 2 out of 10. But if I set that marble aside, I only have 1 orange left to choose from out of 9 total, So that would be 1/5 times 1/9, which is going to be 1 out of 45. And if you want to find out what that is as a percent, that's about 2.2%. And then this last one is purple, then green. So purple was 5 out of 10, so I'm going to go ahead and reduce that since we already did that. And then green would be 3 out of 9, which is 1/3. So that would be 1/6, which is 16.7%. Okay, so again, key here is when you are not replacing for your second probability, your second event, you always have to make sure you change the denominator. If you're also asking for two of the same thing back to back, your numerator will also change. Okay. So that's kind of exhibited in this one as well. If you surveyed 10 people and 8 of them said they like dogs, if you choose 2 people, so you're assuming that if I choose 1, I put that without replacement, but even if that weren't there, we would assume that because you're not going to choose the same person twice. What's the probability that both of them will like dogs? So I'm essentially saying probability of dog, then dog. Okay. And those other 2 people, how dare they? All right, and so my first probability then would be 8 out of 10, right? 8 out of 10 people like dogs. But then for that second person, I'd only have 7 people left who like dogs out of 9 total. So 8 out of 10 is going to simplify to 4/5. And that's going to be 28 out of 45, which is going to be about 62.2%. All right, so this last example is kind of this idea put together though as a table. So we actually won't be finding, the probability will be a little bit different here because we can make some conclusions from the table. So what I mean by that is, so this is a quality control inspector checks for defective parts. The table shows the result of the inspector's work. Find the probability that a defective part passes, okay? And so we are looking only at a specific section of this table. So essentially we're doing like the conditional probability only for the dependent events. So if I know that it's defective, I'm only focusing on this part of the table. So there are 39 defective parts. Of those defective parts, 3 passed. So that would be my probability. So 3 out of 39 will simplify to 1/13, which is about 7.7%. Okay. And then this next one says, find the probability that a non-defective part fails. So I know that this is non-defective right here. So that's going to be 461 as my denominator. And of those 461, only 11 of them passed or failed. So 11 divided by 461 is about 2.4%. Okay. All right, and so tomorrow what we will look at is when you add probabilities as opposed to multiplying them and the differences between those 2 types of occurrences. So if you have any questions, please reach out and let me know, and I hope you guys have a great day.